Hi everyone, this is Kalyan Kumar and welcome back to Chemistry Universe. And this is the beginning of ethers, and there are two videos in this, and these are relatively short videos. The first one is, as usual, the introduction and the methods of preparation of ethers. And remember, alcohol, ethers, and phenols are generally treated as one type of group as they are very related to each other, though they are considered as distinct functional groups. So generally we talk about alcohol, phenol, ether as if they were one, but they're not one, but they're very similar and distinct. So this video is about the preparation of ethers and the introduction of ethers. So let's start with the video. Okay. So we have introduction and methods of preparation. So let's start with the introduction. So what do you think are ethers? Now ethers, what would you say ethers are? And I think most of us who are at this stage of learning ethers pretty much know what they are. They're basically an oxygen bonded to two alkyl or two aryl groups, or one alkyl and one aryl group. You can have any kind of mix. Basically, it's ROR prime. That's what we call as ethers. So ethers are two alkyl and aryl groups joined via an oxygen atom. Now, we can classify these ethers basically in two ways. One is simple or symmetrical ethers, like both sides being the same. Both could be alkyl, both could be phenyl, one could be, and both could be aryl. Aryl is basically a phenyl with some kind of a hydrocarbon attached. And you could even have the mixed and unsymmetrical ethers, where you could have all possible kinds, two different alkyl groups. You could have one alkyl and one phenyl group. You could have one alkyl and one aryl group. You could have one aryl and one phenyl group. So these are the basic classifications. Now let's talk about the bond angle. Now, what do you think would be the bond angle of ethers with comparison to alcohols and water? Now, we have already discussed this in alcohols. And we said that in water, the bond angle is close to 104.5. And in alcohols, it is slightly greater. It's close to, 108.5 because of the steric hindrance of R. In ethers, it increases even further due to steric repulsion and reaches almost 110 degrees. So due to steric repulsion, the bond angle in ethers is larger than in water and alcohol, and this is the bond angle, close to 104.5, close to 108.5, and this is almost 110. Now, if I were to ask you, what would you guess would be the dipole moment of dimethyl ether and diethyl ether? Basically, dimethyl ether is the one which on both sides you have methyl groups. And diethyl ether is the one in which you have both sides ethyl group. So which one do you think will have a greater dipole moment? So, one might say that, there's very likelihood chance that diethyl ether will have greater because it has a greater plus effect. And O is as it is electronegative, it's trying to pull. And if ethyl is trying to push more, then I think the polarity generated in the bond will be greater. So the individual dipole moments of OET and OME, OET would definitely be higher. But when you look at it in totality, remember dipole moment is a vector. And here you'll find that diethyl ether will have greater steric repulsion. So the bond angle will open up further. Meaning that if you have dimethyl ether with, let's say, 110.5, let's make an assumption, 110.5, and it's close to that, diethyl ether will slightly be greater. So what do you think will happen to dipole moment if the angle increases? And since dipole moment is a vector, you know that what happens is there is a cos theta term in it. And obviously, as theta increases, cos theta is going to decrease. So on one hand, the individual dipole moment has increased. On one hand, because of the increase of bond angle, the dipole moment should decrease. But one can always say that inductive effect is not a very strong effect, and therefore the difference between the dipole moments of OME and OET are not that great. So perhaps the bond angle would dominate, and that's what happens. Okay. So the dipole moment of dimethyl ether is more than diethyl ether due to increase in bond angle in the latter. Now, here it's very important to understand some common names and the IUPAC names of ethers. Though we have done IUPAC names separately, but it's important that you know the common names at least. So I'm going to give you some structures, their common names and their IUPAC names. So what do you think we'll call this and a common name? This is called dimethyl ether. And what do you think we'll call it in IUPAC? Well, what we do is we treat one methyl as the parent and this as the substituent. So this is called methoxy and this would be methane. So it's methoxymethane. All right. What about this one? So if it comes to common name, we'll say ethyl methyl ether rather than methyl ethyl. We'll do it alphabetically. And what do you think will be the IUPAC name? Obviously, you have to select a parent and has to be the chain with a higher number of carbon atoms. So it has got 2 carbons. So this is ethane and this is the methoxy group. So it's a methoxyethane. What do you think will happen here? Isopropyl on one side, ethyl on the other. It is going to be ethyl isopropyl ether. What do you think will happen to the common name? Now remember, isopropyl is like this. And you have a ET sitting here. So which is the parent? The parent is obviously this chain. And how do you number it? You number it by giving the carbon with OAT the lowest possible number. Remember, you don't start with this carbon. You try to give it the lowest number because you have to go for the maximum number of carbons in the parent chain. And that can only happen when you take this as 1. So it's going to be 2-ethoxypropane. What do you think will happen to this one? PHOME. So it's going to be methyl phenyl ether. And here you'll always consider this as the parent since it's a benzene ring. So it's going to be methoxybenzene. And what do you think will happen to this one? It's ethyl phenyl ether. It's also called phenitol. And the previous one is called anisole. You have to remember these. And again, this is be ethoxybenzene. Okay. So let's look at for some more. What do you think would be the common name of this? Obviously diphenyl ether. And the IUPAC is going to be phenoxybenzene. What about this one? Now let's look at ring ethers. Now common name is ethylene oxide. It's also called oxirane. When it comes to IUPAC, there are 2 ways of naming this. One is you take these atoms and number them. Number the entire carbon ring leaving the O from 1 to whatever. Then call this O as epoxy and write the numbers on the of the carbon atoms to which this is attached. Now in this case it is attached to 1 and 2. So it's going to be 1, 2 epoxy and alkane would be the parent here. So it's going to be 1, 2 epoxyethane. And now this is one way of naming it. The other way of naming it is make this 1, then 2, then 3 and write it as oxa. This ring oxygen, oxygen of an ether is always called oxa. Oxacyclopropane. Even though it does not have 3 carbon atoms in the ring, since the ring is 3-membered, we call it oxacyclopropane. So that is another way of naming it. Here, now this is called trimethylene oxide or oxetane. Remember these things. And ring, well, if you want to do the epoxy naming, you get 1, 2, 3. Can you see O is attached to 1 and 3? So it is 1, 3 epoxy propane. Whereas if you were to do the other naming, you will say 1, you will say 2, you will say 3, you will say 4. What do you say? Oxacyclobutane. So you don't have to write 1 there because it is assumed that that will always be 1. So what do you think would be this common name? It's very, very important compound. It's quite often used. Most of us don't remember the structure. We remember the name though. It's THF, tetrahydrofuran. It's called oxolane. And from the epoxy naming, you can see it is going to be 1,4-epoxybutane. What do you think would be this? Well, its common name is furan. That was tetrahydrofuran after attaching 4H to furan. And its IUPAC name is also furan. You can use that as the IUPAC name. What do you think would be the name of this one? Well, it's tetrahydropyran, oxane. And the IUPAC name, you can say 1, 2, 3, 4, 5, 5, 1, 5 epoxy pentane. Now, how would you name this one? Now, one way of naming would be that ET is basically CH2CH2, isn't it? So you have two MEs attached. So make the two MEs as substituents and they take this as the parent chain. So what do you think you'll call it? You'll call it 1,2-dimethoxyethane. And if you were to do the other naming, the oxa naming, so you can't start with O now because you have to start from one end. This is 1 and try to give the O the lowest number, 2. And ET will be 3 and 4 and this is 5 and this is 6. So what do you think would be the name? It is going to be 2,5-dioxahexane, even though the carbons are not 6. Now, one may say that why do we need this numbering? Because naming, because it's not possible to use any of these always. For example, what do you think would be the name of this? Its common name is diglyme. But which one do I consider as parent? And if I consider this as parent, what do I call this entire thing? Ethoxy, methoxy, that's going to be difficult. So here the best way is the oxa naming. 1, 2, 3, 4, 5, 6, 7, 8, 9. So what do you think would be the name? It's going to be 2,5,8 trioxanonane. So here you will only have to use the oxa naming. Alright, now let's talk about the preparation. First is the Williamson's synthesis, which is very common. We have already done this many times. You take an alkoxide and you take an alkyl halide and you get an ether. Important thing is that if R prime is R prime X is primary, you only have SN2. But if it is secondary, you will have both SN2 and E2, which means the product yield will be less. And if it is tertiary, you will definitely get E2 because the base is strong. So therefore, it is always important to understand that if you were to ever be asked that a particular ether has to be formed from Williamson synthesis, which one do I choose as alkoxide and which one do I choose as the alkyl halide? Always make sure that this one is that part which can show SN2 much better. For example, if I were to take this and use this, if I use the alkyl halide to be tertiary, and you know that ethoxide is a strong base and tertiary substrates would prefer elimination by E2. So what happens is that you will get alkene here. But if I want to get ether, then I would prefer the alkoxide of this and the alkyl halide of this, as this alkyl halide will definitely show SN2 and I will have nucleophilic substitution happening. Even though this is not the desired method, as the nucleophile itself is highly hindered, so it's not going to be very effective, but then this is the only option you have if you have to do it by Williamson synthesis. And remember, if any of the R's are vinyl or aryl, well, you cannot have any reaction from Williamson synthesis at least. So vinyl or aryl ethers can't be prepared by Williamson synthesis. Now we have studied one more reaction when we did alkyl halides reaction, and that was reaction with Ag2O, dry Ag2O. Moist gave you alcohol. The dry gave you ether. Because the oxide ion O2 minus is a strong nucleophile, and since it has 2 minus charge, 1 minus will replace 1x, by which time you will get this to be an alkoxide, and then it will react with some of the unreacted this thing and form the diethyl ether. So you will get this. All right. So there is another one called the Williamson's continuous ether synthesis. Now here what we do is we take an alcohol, we treat it with sulfuric acid at 140. Remember we did this in alcohols, and then we did Al2O3 also, and that's ether. Now remember, ethers are sensitive to acids and they always cleave in their presence. So this reaction is reversible. So make sure that this reaction is not just one way, it's both ways. And this method is best suited for ethers that have boiling points lower than alcohols, so that I can keep the boiling point in between the two, and the ether forms as a vapor and does not remain in the solution to go back into the alcohol. Now you can use alpha halo ether. That means you can have this where there's a halogen on the alpha carbon and you have RMgX, and there is a nucleophilic substitution taking place, and you will get a different ether. Now you can even use diazomethane. Now this uses an alcohol with a CH2N2. This is diazomethane in BF3, and you'll get ether. Now what basically happens is that alcohol reacts with BF3 because alcohol is not that acidic. So you need BF3 to remove its H. And the reason we need to remove its H is because this is CH2N2, one of the resonating structures. And this C minus takes the H. This C minus takes this H. So this will attack and this will go back. And now you get this and CH3N2 plus. Can you see this lone pair is nucleophilic? It will attack this carbon and the nitrogen will leave. So that's what happens. And you'll get BF3, you'll get the ether, and you get nitrogen gas. All right. So now you can't do this with, you don't need BF3 for phenols because phenols are themselves acidic enough to give the H plus to the C minus. And if you were to use acid instead of alcohol in this case, you'll get methyl esters. And that we will discuss when we do the preparation of esters. And the last method that we have is the Alkoxymercuration-Demercuration. Now we've already done this in alkenes. As we did oxymercuration-demercuration, there we used water, so we got a OH. Here we use an alcohol as the solvent, and we get the product. And then we reduce it, and then you get this ether. So that's it for this video. As you saw, it's a pretty short video. Ethers are not that reactive also. So even the reaction part is not going to be that long. So I hope you understood the preparation of ethers. Watch it as many times as you want. With that, this is Kalyan Kumar saying goodbye and thank you for watching this.